science. Questions?
G is the force of gravity, like normal. Acceleration.
Thank you.
Gravity. And L is just
The length of the
length.
pendulum.
Okay.
Very big.
Yes.
And it could also be an R.
It can also be what?
An R, if we're doing radius or something.
Yeah, typically for the simple pendulum, which is what this is called, they use L, but yeah,
Could be an.
could be R.
So this is called a simple pendulum.
Simple pendulum.
Advanced pendulum.
Galileo hadn't worked through the math of it, but he realized something important there. Recognize that the initial angle is not part of that equation. Not part of omega. I know that frequency, 2 pi times the frequency is equal to omega. So frequency would be omega divided by 2 pi. I know, shocking, but hopefully you'll recover quickly. So this would be 1 over 2 pi times the square root of G over L. The period, I know, is 1 over the frequency. So the period would be 2 pi times the square root of L over G. This is the critical, important thing. We now have a method of timing. G is a value we know pretty well. L is something that I can set. The simple pendulum, you have as close to a massless string as possible, and all the mass is technically a point mass. Ideally, it's a point mass. I make the string a certain length. I don't use my hand to hold it. I have it suspended from something, but I let go. My timing here, I know that if I get it so that the period is 1 second, then I know it gets to here in a half second, it gets to here in a quarter second. So quarter, half, 3/4, 1. I can now get timing down to a quarter of a second. That becomes critical as we start to advance. Galileo is the one who dealt with that, and he recognized that the initial angle did not matter for the period as long as it was small. And apparently, according to legend, he was in church watching the chandelier sway and came upon this realization in church. Apparently he was not paying attention to other things.
So for this to work, what is small?
All right.
I know you said much less than 1, but does that mean negative anything?
No, we're talking magnitude here, not plus or minus.
Okay.
Much less than 1. Typically, when you get the much less than, there's a 10% rule. If theta is under 0.1 radians.
Okay.
And to give you an idea, the approximation.
So T equals 1 over F equals 2 pi root L over G. That gives us the formula for timing stuff.
Yes. It's officially the period of the simple pendulum, which has a point mass at the end, a massless string, and a small initial amplitude. There we go. If sine of theta is different from theta by 10% at an angle of 44 degrees.
Anything below 44 degrees.
So at 44 degrees, typically 44 degrees is not considered to be a small angle, but to give you some idea, you've introduced 10% error if the initial angle is 44%. That's 44 degrees. 5% off at a little over 31 degrees. In physics or math, typically you want under 5 point something degrees.
So
But
really
a
small.
radian is 50 something degrees.
Right, so really small, like
Yeah.
below 10 degrees basically.
Yeah, yeah. I did in Physics 133, we were doing some optics experiments, and the small angle approximation was being used. And when we stopped using the small angle approximation, we were off by like 1% of prediction. With the small angle approximation, the farther out we got, the more off we were, as you would expect. But I think we're on 15% error, 20% error at the wider spots.
Which is good.
Well, considering without using it, we were 1% off. It depends on to what you want to compare it.
But while using it, it was a lot easier.
Oh yeah, the math's a lot easier because if you didn't use the small angle approximation, then you need to somehow come up with a relationship between sine of theta and alpha. Which means that you're using the longer approximation of sine of theta. Sine of theta is equal to theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, and so on.
Obvious.
So if theta is small, that's your approximation. If it's kind of small, that's your approximation. If it's a little less than that, and you just keep going out however far you need to get to be more accurate.
Just use an exclamation.
Factorial?
Yeah.
You're not familiar with it?
We're getting.
It's everything multiplied by just like the number.
It's just, you multiply everything from.
1 times 2 times 3 times 4 times 5. So whatever.
Yeah, 5 factorial is 120 because it's 5 times 4 times 3 times 2 times 1. This is 6. And one of my students, my first year, came up with equestorial, where you multiply it all the way down to 0. So 3 questorial would be 0.
Wow.
Everything questorial is 0.
Did you use a question mark?
That was his suggestion. I think it was the same student who suggested when you talk about snap, crackle, pop, and then the one after that, I think he was the one who suggested splat was appropriate. Anyway, we are past time. Thank you for my indulgence. I thank you for your indulgence. You're indulging my indulgence. Thanks.
Do you think we're gonna have, like, between the time of, we take test 2 and the time like the semester is over, do you think we'll have time for corrections for that? Like, how long do you think that period's gonna be?
All right, you're gonna take the last calculator test Wednesday of next week. Semester's over on Friday.
Yeah.
So I get a day to do correction, or?
There's no
great.
corrections on the last one.
It is.
I've had students try to talk me into doing corrections on the last test. Over the years, there have been a couple classes where I've done that. It has never made any difference whatsoever at that point.
Okay. All right.
But if you want to spend your time doing something that won't help you at all.
The encouragement is, it's just,
So-
peaked right there.